Okie dokie. So homework for today was what? Selection sort reverse? Something along those lines. Let's take a peek, and then we're going to look at, I think, binary search is next on our docket, but we'll make it a game time decision. Oh, and for any of you who's noticed, in the back of S109, we have a new, we have this VR chair that's in there that is now set up for mobile and PC-based VR, fully immersed in this chair like turns and stuff on its own, and you can like feel the stuff that's happening. It's pretty legit. Well, it's for toys. The other, the laptops are for the robotics and security lab, but yeah, I mean, nothing says you can't use it. But in any case, we'll be doing a VR demo one of these days. We do have like a face thing for the VR things that we can clean in between. And then we also have infrared antibacterial thing we put the whole headset into, and I don't know, UV light clean it thing. So we should be fairly COVID safe. We're just making sure the protocols are accepted before we do the demo. But Half-Life Alex on that VR rig is kind of ridiculous. like that's the way VR should be done, completely wirelessly from the PC in a chair that moves whenever you turn your head. Yeah, it's pretty good. Look forward to that. All right, this is not our class. This is 250, right? Okay. All right, so we look at, well, let me just read the homework. So homework for today was given the algorithm for selection sort, which we have right here.
Sorry, you're not sharing your screen.
I literally was just thinking that in my head. Thank you. Now you can see it, right?
Yeah.
So in any case, this is the algorithm for selection sort. We'll come through it here in a second. So implement another sort method in our card parser. So we wrote a couple different ones so far that sorts using the selection sort algorithm, but this time sort from highest cost card to lowest cost card. So you have to make a little modification and then give us the GitHub link and that stuff. So let's look at this algorithm here. So for selection sort, we're going to start off at the beginning of our array. So minimum position will be 0, location 0. Then we're going to search for the minimum element in the list and then swap it with bucket min. Increment min to point to the next element, repeat until a list is sorted. Now, one thing you might notice here is this is kind of similar. This is almost a hybrid between our brute force approach that we did initially, right? And the, shut up. I'm gonna throw stuff. Hold on, I'm throwing stuff. Will this mouse break? All right, so it's kind of a hybrid between our brute force approach that we wrote initially, where we said, find the smallest value, remove it, put it into a new list. Find the smallest value, remove it, put it into a new list. And the insertion sort that we wrote last time, which goes through and swaps things towards the beginning of the list. Now what we're doing is we're kind of joining those things together and getting the find the minimum value over and over again approach, but doing it all within, in line sorting with your original list, okay? And then repeat until the list is sorted. The list would be sorted once we get to the end of the list, right? All right, so let's get Eclipse open here. My webcam is not on. There we go. How do I look now? No comment on that way. All right. So we're inside of our card parser, and we're going to go ahead and write a new function in here. And we're going to call this guy selection sort highest cost to lowest cost. All right, now I think we already have a function called find smallest, right? So that would go hand in hand with how the initial find the smallest value thing would work. But we wrote this original find smallest to work with our hard-coded version, our brute force approach, where we actually did use it to remove from our minions. But in this case, we're actually interested in finding the largest value. So we're going to write a little tool that will go find the largest value card in our list, starting from a certain position. Okay. We'll say private Hearthstone card, find largest from position in pause. All right. And this guy's job will be to find the largest cost card from this position forward and return it. Find the largest cost card from this position forward and return it. Now, realistically here, so I'm going to leave it like this at first, and then we're going to doctor this a little bit more. Okay, so let's just start with this logic. So the only problem we're solving right this second is to go through my collection of minions, starting from position pause, and find the largest card that's in there. That's all we're doing at first. So we're going to keep track of a Hearthstone card. We'll call this Kerr-Winner again. And this will be this dot the minions get pause. The first element we're looking at is the current winner. Okay. And this is Hearthstone card. Similarly, we'll say index of our winner, because that's going to be something we might be interested in. It's going to start off at pause. Now we want to go through our array, starting at position pause +1 all the way to the end, seeing if there's any more big cards. So for int I is equal to pause +1, keep going as long as I is less than this dot the minions dot size, I ++. Each time through, we're going to ask if the current card we're looking at cost is greater than the current winner's cost. Kerr-Winner dot get cost. That means we have a new winner, right? If the cost of the guy we're looking at is greater than the cost of the guy that I currently had is in the lead, we have a new winner. What do we do when we have a new winner? We set Kerr-Winner equal to this dot the minions get index I, and we set index of all right. That's what we do if we found a new winner. Whether we found a new winner or not, we're going to move on to the next value. We're going to do this over and over and over and over again until we get to the end of our list. And then when we finish this for loop, we know that Kerr-Winner is the card with the highest cost starting at index pause. And we know it is found at index of winner in the minions. That makes sense? Okay. Now, based on our current rules for this method, we will then say we're going to return card winner. That's the largest card from a certain position in the list. Now, the reality is that this guy is going to be a support tool for us for our selection sort, right? So, and let me show you why. Before I fix it up here, we're going to go write our selection sort. So here's our selection sort, highest to lowest. Now go back to our algorithm for selection sort. It says set minimum at location 0. We're going to keep walking our list all the way to the end. So we're going to say for int min is equal to 0. Keep going as long as min is, and actually I'm going to rename it to max. Keep going as long as max is less than this dot the minions dot size max plus plus. Instead of the minimum values being early, we're finding the maximum value being early. Okay. Now, each time through, we want to find the largest value starting at position max. This dot find largest from position max. Now, this is going to give us the largest card. So if I just go ahead and say Hearthstone card, call it the max, is equal to this guy. So right now I have the largest card, correct? From my position max. Now I know that this is the card that should go at bucket max in my minions list. But I don't have the information I need to do the swap. We go back to our algorithm here. The algorithm says, search for, in our case, the maximum element in the list, and then swap that value with location, in our case, max. What I have out here is I have now access to the card that is the maximum card, but I don't have access to where it was. Does that make sense? So I got some options. So here, I'll ask the question here. Let's assume so we'll make this a challenge. Let's assume that we are not allowed to do our swap inside of find maximum. That's ultimately where we're going to do it. But I'm tying one hand behind our back for a second to show us something. All right, so let's assume that we're not allowed to actually do the swap inside of find maximum. Rationale being, if I look inside of find maximum, or find largest from position, I have the winner and the position where it's at. I have the information I need, okay? But we're not allowed to do that for this example, for this challenge. So let's assume we're not allowed to do our swap inside of find maximum. Find largest. How can we make find largest return all of the information that we need to do the swap inside of selection sort? Make sense? The question I'm asking? So back in here, I can't swap in here. It's against the rules for this challenge. It just so happens in here, I have the two pieces of information I'm going to need. When I get down here, after this for loop, I know that index of winner is the position where the biggest card was, and I know that cur winner is the biggest card. I have everything I need in order to do the swap inside here. But what I'm asking is, if we're not allowed to do that, how can we make find largest return all the information we're going to need for doing that swap? So imagine that there's some world where you're solving some problem where you need to return more than one value, is really the example we're working on right now. Okay. We'll go back in here. So what can I do in find largest from position to make it so that it returns more than one value using only what I've taught you before? I'm not asking you to come up with some sort of deep-rooted Java secret or something like that to do this. I want to return more than one value. How do you think we can accomplish this? Okay, I can put it in one string and abstract it. Okay, so he's suggesting that we have it return a string. Okay, instead of our cur winner, which is a card. So string answer is equal to, help me take cur winner and index of winner and put them into a string. In real life, we're a magician at this point, right? I have a Hearthstone card in one hand. I have a number in the other hand. Okay, this is the real life example here. I'm about to perform a magic trick. I'm about to slap my hands together and hand you a string. How do we do that in real life? Can we pull that off in real life? Can I turn this thing into something it's not, and this into something that's not, put them together and turn them into something completely different and hand it to you? Doesn't seem like we can pull that off in real life, can we? I can't take a quarter and a spoon and hand you $1 from those two things. So sounds good on paper that, hey, we like strings. Java is a string-based language, so certainly a decent place to go first, right? Say, hey, if we can get this in a string format, maybe that'll work out okay. Okay, but now you're not lost yet, technically. You could go that route of a string. Anybody want to take a stab at how we could convert this to a string and then rebuild it later on? It's not the way we're going to end up going about this, not the direction I was going, but if you're just really set on making this guy, turning this all into a string, go ahead. Copy and paste the content. Tell me about that.
After you run that, you get the information from it, you copy and paste it. But that would kind of go against the rules.
Well, what do you mean copy and paste?
Like, when you output it and output information, you get copy and paste that.
And then what? So copy and paste it, then go write the program again with that string. Yeah, but that our program won't work then. Well, this program should run on its own, right? It shouldn't stop in the middle and say, okay, user, go ahead and copy this thing, then go to line 17 and paste that string in and then run it again. Run it again. I wouldn't call that a program anymore, probably, but what do you think? Remember, this is what a Hearthstone card is, right? A Hearthstone card is a name, a cost, an attack, and a defense. So I could give myself a second way of building a Hearthstone card, right? I could give myself a second way of building a Hearthstone card, and I could then create a constructor here. So let's call this public Hearthstone card. And this guy takes in a string. We'll call this card string. And then what we do is we create a string array called parts is equal to card string dot split on maybe the comma. Something like that. That does mean that we can't have comma in the name, but we'll just say that's okay. If you really want to be extra defensive about it, we could do something like do our split on that instead of a comma, but we'll do comma on this. And then we can say this dot cost. Let's assume we get the name first. So we'll say this dot name is equal to parts at bucket 0. This dot cost is equal to integer dot parse int parts at bucket 1. This dot, and I'm going to steal this. This dot attack.
He no fucking police officer.
He what his daddy is.
He gonna say his daddy is not, nigga.
That's all important.
I'm gonna be around you then. I'm gonna find him a new daddy.
Okay.
You don't think I can find one?
But the nigga ain't gonna be.
I don't want to just let it keep going.
Exactly, that's the fucking point. If I wanted you, I would get
Okay, whose computers are coming from?
what?
Let's find a nigga that's better than me.
Okay. You just better than all the niggas doing?
Nah, I'm not better than all the niggas. Just the niggas you choosing.
Fuck you.
It was Reese? It was Adam? Who was the culprit? All right, disclaimer, there might be some questionable language on today's recording. All right, so in any case, we'll keep trucking. Yeah, so keep yourself muted unless you have a question. Maybe don't watch movies during class. Either one of those is probably good practice. All right, so what we're doing here is we're creating a second way of creating a Hearthstone card. I can say, hey, you know what? I can pass in a string that I've formatted in a special way. You know, we're really forcing the issue here. I'm going to pass in a string, and I'm going to go ahead and split that string on commas, presuming I've built it by gluing everything together as commas. And I'll go ahead and set the name equal to whatever was the first part. The cost is going to be the integer version of the second part. The attack will be the integer version of the third part. The defense will be the integer version of the next part, something like that. So now I've taught myself a new way of creating a Hearthstone card. So now what I'm going to do is we're going to go back into card parser. For find largest here at the end, we've advertised we're going to return a string. So what we're going to do is we're going to build a string out of a Hearthstone card. So why don't we go ahead and teach a Hearthstone card how to convert itself into a string format. So let's just do a public string, 2-card string. And this guy will return the empty string concatenated with this dot name, concatenated with a comma, concatenated with this dot cost. Concatenated with a comma, concatenated with this dot attack, concatenated with a comma, concatenated with this dot defense. So that would return a string in the format that we are assuming we have from this Hearthstone card up here, right? So now I can ask a Hearthstone card to give me the card string version of yourself. And what he does is he hands you, this is kind of like JSON, right? He says he's going to hand you, well, here's a string that represents me. It's going to have my name, followed by a comma, followed by my cost, followed by a comma, followed by the attack, followed by a comma, followed by the defense. So now out here in Card Parser, I can go ahead and say string answer is equal to cur winner, which is a card, dot to card string. And then I can concatenate onto that maybe a colon, and concatenate onto that index of winner. And then I can return answer here, right? So then out here in my selection sort, I'm going to receive a card string. Well, I'm going to receive a answer string. And the first thing I'm going to do is I'm going to create a string array called parts and set this guy equal to answer string dot split on the colon. The first part will be my my card string. The second part will be my index. Then I'll say int index is equal to integer dot parseInt parts at bucket 1. And then I'll say Hearthstone card C is equal to new Hearthstone card parts at bucket 0. Parts at bucket 0 from that guy will be the string that is the name, comma, cost, comma, attack, comma, defense. Parts at bucket 0 will be my 13, the position in the array where this value is found. All right. And then now that I have those two pieces, I can now do my swap, sort of. So I'm going to ask the question here. Well, so first of all, before we go any further, recognizing that this is a super roundabout way of doing this, right? Okay. But, you know, hey, we're MacGyver here. We're solving the problem in terms of the stuff laying in front of us. Our initial mentality said, hey, I want to work with strings here. That's the rabbit hole we jumped down is the punchline, okay? So I said, okay, well, how can I get a Hearthstone card into a string? And now I already have my index. Can I glue those together somehow? Yes. And I kind of said my card string is separated by commas, and then my index is over here. I'm going to put a colon between those so that later on I can split them into two and then build a new Hearthstone card out of the card string and then get an integer out of the index. All right, makes sense so far what we have right now? All right, so now the question is, or let's see, does C hold the identical value to what cur winner held inside of find largest? Reminder, inside of find largest, cur winner was our Hearthstone card. We went through there. Ultimately, cur winner is going to equal the Hearthstone card with the largest cost, right? That's what this guy will ultimately equal in the end. But I return this weird string thing. Up here, I then split that string thing back apart. I'm sorry, not there. Here, I split that string thing back apart, and then I got my index, and I built a new Hearthstone card with the first part using my new constructor I built in here, which knows how to take in a card string, split it into a comma segments, and then set the fields here. So my question, again, is does this card C hold the identical value to what Kerr Winner holds in here? Why or why not?
I would say no, because there's no way of knowing which one's the largest.
It's not a random card. We returned the card string version of that guy. I mean, if you want to see what it looks like, here, we'll interject for a second here. I'll go into my card parser and let's just get the largest card only. So I won't call this guy, I won't call this guy. Instead, I'll say CP dot selection sort highest cost. Actually, let's do this. CP, well, we're going to end up calling our selection sort. So we'll call our selection sort from there inside of card parser. Right now, our selection sort is doing some of this stuff. I'm going to have it not. Well, actually, we'll just have it go through one time. That'll force it to just go through one time. In fact, we'll really force it to just go through one time. So now we're going to get a single answer from find largest. Should be the biggest card in there. But we're going to get it as an answer string. And I'm going to go ahead and I'm going to print out system.out.println answer string. So we'll see what that guy looks like. Similarly, we'll go ahead and we'll print out index. And we'll print out parts at bucket 0. And then ultimately we'll ask that card we just built to display itself. So I'm going to go ahead and call selection sort, highest cost to lowest cost. That guy's going to come in here. He's only going to go through this loop once. So for right now, you can just pretend like there isn't even a loop there. I just kind of, short circuited it to give us some examples. So I'm going to basically do this stuff right here one time. I'm going to get my answer string from find largest position, and we're going to see what that looks like. We're going to see what the thing that I'm returning from find largest is. Okay, because your contention was, oh, we're randomly getting a string. You're going to see it's the largest string. It's a string representation of the largest card. Okay, then I'll go ahead and split it. I'll show us what the index is. I'll show us what the card string part of it is. I'll go ahead and build a card out of that card string, and then I'll tell that card to display itself. All right, and if we want to take one more step here, so I can really trick you. Before we return our answer here, I'll go ahead and say curwinner.display. So I'll tell the actual Hearthstone card that was the biggest one to display himself. Then I'll return this special string thing. Then I'll pull that string apart, show you the individual pieces. Then I'll build a new Hearthstone card out of one of those pieces, and then I'll display that. It should look like the same card. So here's would you agree that looks like the largest card, largest cost card? Okay. So that was Kerr Winner inside of find largest at the end. This is the string that was returned by my find largest. Notice the first part of it is what I'm calling a card string. That's the name of the card, the cost, the attack, the defense. and this is the position where it lived. This is the value that I'm returning from find largest. So I've effectively encoded the two pieces of information, the stuff about the card and the place where it lived into a string. Okay, and I've returned it. Now I've proven that I can get the pieces out of it. So here's the index, 294, and then here's the card string part of it. I then built a new Hearthstone card with that card string. Remember, I created a new constructor inside of Hearthstone card. So now there's two different ways I can build a Hearthstone card. I can build it by giving it 4 individual pieces of information, or I can give it a single string formatted in a certain way and let that guy, so it's formatted like this, and let him go ahead and split it into the 4 pieces, then displaying this card. So does that card look the same as this card?
Yeah.
The question is, are they identical cards? That's the question I'm asking right up here. Does C, this card that we just displayed here, this is C. Sorry, this is C. Does that guy hold the identical value to what Kerr Winner, which is right there, held inside a find largest value? Go ahead. Different spot in memory. It represents the same card, right? It's got the same data. Well, I have 2 copies of this card. I have this place in memory, which has all this information about Golemag, and I have this copy of memory that has all this information about Golemag. They are different places in memory. So doing a swap with these, in this case, because of the nature of the situation, would actually work, but it's going to be memory inefficient, because now in order to swap 2 spaces in here, I'm going to effectively say, I'm going to create a brand new card that is a copy of the one that I want to swap, and then I'll overwrite stuff, ultimately abandoning old memory, creating new memory, overwriting the same contents, not the same value, but the same contents. That makes sense? So we're kind of seeing how this different stuff could ultimately work out. Now, this is how I can get all that information inside of our selection sort, highest cost to lowest cost. Now, here's a follow-up question though. Even with this in mind, do I need to have the actual card in order to do a swap? Or do I just need to know where the largest card lives? Could I come into card parser here and say, find position of largest, let's call it largest cost from position, and have this guy return int, and maybe instead of position, let's call it index. Find index of largest cost from position. So in the end, we'll go ahead and have this guy return index of winner. This is where the largest card was found. I can go to that place inside the minions to find the actual card. Can I? So I only need this guy to return that single value, the int. Or I could do the swap inside here if I wanted to. But now I have a generic function that might be helpful, right? If we look at our other function where we did find smallest, this guy was very much built in terms of needing to make it work for our brute force approach to our original sort. All right, we made it work for that because this is the guy that ultimately did the swap. So now what we're going to say is let's keep this generic. At any point in time, I can ask this function to tell me where in the collection I can find the largest cost card given a starting point. And that's all he does. So now up in here, find index of largest from position max. All right, so and this guy is going to be an int max index. That's the position of the largest card. I now need to swap that with the value that lives at current position max. So I'll say Hearthstone card temp is equal to this dot the minions dot get position max. This dot the minions dot get position, I'm sorry, dot set position max equal to this dot the minions dot get max index. Then I can say this dot the minions dot set max index equal to 10. So this will actually do the swap. Starting at bucket 0, find the position of the largest value starting from position 0. I'll go ahead and then retrieve that card, the maximum card, which is our, well, this is our current max, the starting point. So I'll retrieve that into temp, preserving that. Okay, so the first time through, I'm going to preserve whatever's at bucket 0 inside temp. The second time through, whatever's at bucket 1 inside temp, whatever's at bucket 2 inside temp, so on and so forth. So I'll preserve that card from position max. Then I'm going to overwrite position max with the actual card found at max index, which might find largest cost from position returned. Then I'll overwrite the card that lives at max index with that card I preserved, temp. Then I move down the line over and over and over and over again. Starting at bucket 0, find the maximum, swap it. Starting at bucket 1, find the maximum, swap it. Starting at bucket 2, find the maximum, swap them, so on and so forth. Make sense? So now out here in driver, if I go ahead and I call my selection sort highest to lowest, and then I call my minions, I should see at the very bottom the lowest cost cards. That does not look highest cost to lowest cost. Let's just make sure I'm calling the right stuff in here. Selection starts max off at 0, goes through the entire collection of minions, max plus plus, find the largest card, that's max index. Make sure I'm returning this right stuff from down here. That's going to be our index of our winner. That's fine, that looks good. Oh. It is. Thank you. That was artificially exiting this loop, so I actually only went through it one time. There we go. There's our cost 0 stuff, and then above cost 1 stuff, so on and so forth. All right, make some sense? Good.
How does it cost 0 for the Hearthstone? Are they just like a decimal of the cost, or is it just like?
No, it's free. Yeah.
Oh, okay.
But presumably the card doesn't maybe do all that much. or, you know, it's something that's like a filler thing. Sometimes there's a couple of cards where it's a minion or something. Yeah, I mean, well, these are zero cost minions. This just seems like cheating though. You know, a zero cost minion with 4 attack, 4 defense. That card's broken. What's up? Depends on the card. I mean, like rogues have a zero cost card called Backstab that will do 2 damage to a minion, an undamaged minion, and presumably to kill it early on in the game or something like that. But that kind of makes sense for a rogue. They might have like kind of a freebie, just kind of, just, you know, stab somebody real quick and they're dead and move on. Yeah.
So what's that called?
It's called mana in the game. It's a, you know, a currency that it costs to put the card out. The first round you have 1 of those. The second round you have 2. Then you have 3. Then you have 4. So that's like every turn you have an amount of mana that you can spend. So you have to use your cards in the right order. And whenever you play a card, it has a cost, and that's the number of mana you're gonna have to spend to use it. So if you're on turn 4 and you have 4 mana, you can't play a 3 mana card and a 2 mana card because that costs 5 mana. You're out of currency. You have to wait till the next turn to play both of those in the same turn, that kind of stuff. Sure. A lot of the games are kind of like each other, aren't they? I mean, isn't that the idea is you have these different games, and they take the genres that work. I mean, if you're a gamer and you like first-person shooters, you have a collection of 20 first-person shooters you can pick from that, you know, has their own little nuances, but at the core of it, it's the same game, right? Same kind of game. Same thing with this. This is a collectible card game, a trading card game. They all pretty much share a common concept, and then they have their differentiating factors that might make you like one over another one. League of Legends is a MOBA, you know, so if you like League of Legends, the competitor from Blizzard is called what? Heroes of Azeroth? Is that right? Heroes of the Storm. First person shooters, Blizzard has theirs. Call of Duty is kind of like maybe the current poster boy, something like that for first person shooters, but I don't know. But, you know, so you have these different genre games that all kind of mimic each other. All right, so homework for next class is we're going to look ahead to something called bubble sort. I'm sorry, not bubble sort. Binary search is what I'm looking for. So I'll just drag this up here. Given the algorithm for binary search, implement a binary search inside of what I call it, card parser. It allows you to search for a card by its attack. For example, if you gave it the value 5, it should return the first card it found using binary search that has a attack of 5. Note that binary search requires that our data be sorted prior to searching. thing that we have several sort functions we have written to use for this. So submit the GitHub link and the self-eval. All right. Questions, comments, concerns, bribes. So we're practicing. You're going to go and learn about the binary search algorithm. You're going to then implement it yourself in Java, and then you're going to prove it worked. And we're doing this based on the attack. We're searching for the attack values of a card. You're going to prove to yourself that it worked by calling it, passing it some value to search for. Questions, comments, concerns, bribes? Go ahead. Yep. Desktop. All right, I will see everybody on Wednesday, and I'm updating my code now. Updated code for completed selection sort. Ready for binary search code. MOBA stands for Massively Online Battle. What's the A? Battle Arena.
Have you ever gotten that thing that costs it 50?